All right, so the symbolic math toolbox is really useful, especially for you in all of your math classes and the type of math stuff you need to do for your coursework here. And it's actually, one of the big reasons why Dr. Wang likes to have this course as a prereq to robotics 4200 is because he does a lot of this symbolic math, manipulating, polynomials and doing common denominators and stuff. There's a lot of really nice symbolic math things you can do. And like I've talked before about this whole thing between Mathematica and MATLAB, that Mathematica in general is more on solving mathematically things symbolically and analytically, and MATLAB traditionally has been more in terms of numerically solving things. And so, the difference between numerical and analytically solving something, in an analytical solution, you write the equation, you manipulate the equation, and you get an answer that has an algebraic answer, and then you plug numbers in and you have the exact solution. Okay? Whereas a numerical approach is going to approximate that some way. And one example that we've already done is that the trajectory of that guy being shot out of the cannon, that the height, we basically find what is the y value for lots of times and choose the biggest one that occurs. Okay? And that's going to be an approximation, because unless you choose a time at exactly the point when he's at the peak, that y value is not going to quite be what the peak is. So that's going to be an approximation, but as long as you evaluate at lots of times, it's going to be close enough that no one's going to care. Okay? Had you solved that problem analytically, symbolically, you would have taken the derivative and set it equal to 0 to find what is the peak time, and then plug that analytical peak time in, and you would get the exact solution. Okay? So, there's different ways you can solve things analytically or numerically, and like I said, in your classes, in your math classes and many of your engineering classes, the problems you are solving are simple enough that an analytical solution exists, first of all, and is not too terribly difficult to get. Many real-world problems either do not have an analytical solution, at least none that no one knows, or it's so painful to get the analytical solution, it's better to use a numerical approach. So take it with a grain of salt. The symbolic math toolbox can do a lot of things for us, but it can't do everything for us. And in this nice sanitized world of your education, the analytical and symbolic solutions are going to seem the most appropriate for all of your problems, but eventually once you start getting to bigger problems, numerical solutions might actually be the best way to go. Okay? So, to use the symbolic math toolbox, we need to tell MATLAB that we want to have variables that are not going to be standard computer science variables. I mean, a variable is basically a name that gets a memory location, and there's a number or a thing that's stored in that memory location. That's what a variable is in computer science. A variable in mathematics is not that thing. Okay? We need to tell MATLAB that we want to have a variable that has the mathematics definition and not the computer science definition. And we do that by using the command symbs, which stands for symbolic variable. Okay? And we can say, for example, I want to have y and x be symbolic variables. And what you'll notice is now x and y exist, but they do not have a data type that you're used to seeing. It's not a double like a normal x and y would be. Like if I say z is equal to 5, z becomes a double. But x and y are symbolic data types. So if I just type x, it's just x. X is equal to x. It's representing a mathematical variable x that could be anything. I mean, that's what a mathematical variable x could be anything. Right? I mean, if you have y as a function of x, it could be just anything. Well, we could do that. Y is equal to sine of x. And y is just equal to the sine of x. You can see there. I mean, y is still a symbolic variable, but what y is equal to is the sine of x. But x and y don't have any specific numbers. which normally in computer science, y and x would have to have specific numbers, but these are mathematical variables in the mathematical sense that they could be anything. Okay? And after I've tortured you with the plot command and having to send an array of variables, an array of x values, an array of y variables, and then formatting, string, and all that stuff, I've tortured you with that. And then there's this really amazing thing called easy plot. Well, plot y. Well, there's y. I mean, I told it that it was sine of x, and it's like, okay, it's sine of x. I'll go ahead and plot sine of x. So this is really cool. So you can create some function. You say y is equal to sine of x. You can say y is equal to sine of x times cosine of x. You can make this be some compound function, and then I can do easy plot of y. And again, that's what sine of x cosine of x times sine of x is. Okay, and you'll notice it chose what the domain was. It said, well, he didn't tell me what domain. I just picked one. Okay, if you want, you can specify what the domain is. You can say I want to go from 0 up to 2 times pi. I think that's the way it works. No, I guess I need to make that yeah, I don't use easy plot very much, you can see. Okay, but if you send 2 arguments to easy plot, the first argument being the symbolic function that you want to plot, and then the second argument being an array of 2 values, one being the minimum x and the other being the maximum x, you can see I'm going from 0 to 2 pi now in my plot. 3.14 times 2 is 6.3 or something like that. You can see it goes up to 6.3. Okay, so we have this wonderful thing, easy plot. Okay, we can have y be other things, like let's say we make it be a polynomial. Y is equal to x squared minus 2 times x plus 7. Okay? And then, of course, I can do an easy plot on that. I can do other things. Like I can say, well, factor y. Apparently that one doesn't factor. Okay, let's try another one. Let's try one, maybe. Surely that factors. It doesn't. Well, let me go the other direction. We can do let's say y is equal to x minus 2 squared. And then if I do the expand function on y, it will expand it out. Okay, that's kind of neat. I mean, this is kind of middle school math type stuff, but it's useful. It does things for you that otherwise you have to do by hand. So now, if I then did factor on that, it will bring me back the other way. Okay? So if I do a factor on that, it's telling me, well, if I factor this thing, then I'm going to get x minus 2, and you'll notice, that's how I created it. I created it by having y be that thing squared. First of all, then I expanded it into that, and then I took the expanded thing and I factored it back. Now this is kind of interesting. What is the result? It got stored in ants, which is what happens if I don't catch it anywhere. But look what ants is. Ants is a 1/2 sim. It's an array of symbolic variables. Okay, and you can see that in the response here. You can see the brackets, the square brackets. Square brackets, that usually designates that there's an array of something. We're used to seeing arrays of, doubles. That's an array of 3 doubles. This thing here is an array of 2 sims. Okay, so let me go back to the factor thing here, and let me catch that in Z. So now it's not in ants anymore, but it's in Z. So I can say, well, what is Z1? Well, the Z1 is the symbolic expression x minus 2. What is Z2? Well, that's also the symbolic expression, x minus 2, because they're the same thing. Okay? So this is kind of weird that we're used to having arrays of doubles, and suddenly have an array of something else. Now, we have had arrays of other things. We have had arrays of characters. For example, this is an array of characters. It's an array of chars, and I can say, what is the third Q? Well, the third Q is that E right there. Okay? So here's a case where I have an array of something that's not doubles. So having an array of symbolic things shouldn't be that strange, okay? It's just a different data type. I can have an array of any data type. Just like in C++, I can have an array of point class objects. And we're going to do that in Python too, where you're going to have, they're going to be called lists, but you can have a list with anything in it. Okay? So we've got this situation where we're having arrays of symbolic expressions. Okay. So we've done the factoring polynomials, expanding polynomials. We've done the easy plot. Okay. We can also have y, and this is a little weird, that we can have y be x squared plus x minus 4 times minus x equals 7. Now this one's kind of weird because normally when you write the equal symbol, that is checking for equality. You're going to ask, is the left-hand side equal to the right-hand side? That's normally what double equals means to us. It does not mean that in this situation because we have symbolic expressions. The thing that's on the left and the right hand of these equal sign in this case is a symbolic expression. Now I'm not sure, but I think the reason why they're doing this is because if I want to set, you know, what's interesting here is that previously we had y be some function. Y is like a function of x. And here y is not a function of x, but y is an entire equation. Okay? Y is the equation x squared plus x equals 7. And if I want to set y equal to the equation, I use the single equal sign as the assignment operator. And so I can't use the single equal sign here to say that I have one side of the equation and the other side of the equation. So they just said, well, if I can't use the assignment operator single equals, well, I'll just use the double equal symbol. It just gets a little confusing. But when you use the double equal symbol, when you're in working with symbolic expressions, it's saying the left-hand side of the double equals is actually equal to, in a mathematical sense, to the right-hand side. So now y is an equation in and of itself, okay? And I can use the handy-dandy solve command to solve y. And I can solve y, and those are the two results of solving y. Those are the two roots of that polynomial x squared plus x equals 7. There's actually another way I can do, I can solve for the roots. I can pass to it the coefficients of my polynomial. That's another way that I can solve for the roots. And you know, it's a little bit different. Basically, what roots does is this is the x squared, that's the x squared coefficient. This is the x coefficient, and this is the 0th order coefficient, which if you use the roots command, that has to be on the same side of the equation. That's why it's minus 7. You get x squared plus x minus 7 equals 0. So roots assumes that you've rearranged it so that your polynomial is equal to 0. Now, you can see here, when I do roots, it gives me a numerical number. When I do solve y, it gives me an analytical expression. That is actually still a symbolic expression. If I say z equals, and if I look at what z is, okay, z is a 2-by-1 sim. Okay, it has two rows and one column. Okay, so this is actually a symbolic expression. It's not a number. Okay, if I wanted that to be a number, if I wanted to convert a symbolic expression like that into a number, I would need to convert z, which is a symbolic expression, into a double, which is a different data type. So when I convert z into a different data type, you can see then I get the actual numbers, which gives the same thing as what the roots did. Because roots is going to give you a numerical result. The solve, when you pass to it a symbolic thing, it will return you symbolic stuff. Okay? So this is kind of neat. I can use this solve, if I have an equation like I have here for y, I can use the solve command to solve that, which is really interesting. Okay? I can even do something like this. Y is equal to a more complicated equation. Sine x plus x equals 1. So here's a different equation. X plus sine x equals 1. Okay? That's the equation x plus sine x equals 1. And there is, presumably there exists some x for which this equation is true. And if I do solve y, it will give me the solution. Now here's a really interesting thing that happened. Okay? It said, warning, cannot solve symbolically. I'm returning to a numerical approximation instead. Here's a situation where there exists no analytical way to solve that equation. There's no, maybe there's a known way to do it. I'm not sure. But if there is a known way, it's very complicated. And so MATLAB gave up. MATLAB tried to solve it symbolically and give you a symbolic result, but it gave up and said, well, screw it. I can't come up with a symbolic expression, so I'm going to come up with a numerical approximation. So the number that it has here on the screen, all of these digits here, that's not the actual analytical solution like this thing. See, this is an analytical solution. The square root of 29 divided by 2 minus a half. Okay? That's an analytical expression that is exact. Okay? Whereas this negative 3.1926, that's a numerical approximation. So unfortunately, this equation doesn't have any handy analytical solution, but it didn't just say, sorry, I can't do it. It went ahead and gave you a numerical approximation. So already here's a case where you can't solve everything symbolically. It had to go and solve it numerically for you, but at least it did it, and it did it automatically, and you didn't have to do anything extra. Okay? So that's pretty neat. So I'm sure going in your heads, there's all sorts of ways you're thinking, holy cow, I can use this in all of my math classes and do all this algebra and all these things that could really help me out and ease up some of the burden of solving things into my math class. Of course, you can't bring in, your computer with MATLAB when you go into your test or anything, but at least it can help you gain understanding, and at least in your engineering classes, it can help you speed up doing the math that you on a homework problem or a project or something, it make that math easier for you. Okay?
TI-36 does the same thing.
What's that?
The TI-36.
The TI-36 will do similar things. It can solve things symbolically.
You hit a button and it'll change it to numerical.
Right. Okay. So calculators nowadays are little miniature computers, so they do a lot of these types of things. So yeah, that's great. I mean, I haven't used a calculator in, I don't know, maybe 15 years because I always have my computer in MATLAB, and so I don't know all what the fancy calculators nowadays will do.
They frown upon a laptop in the FE.
Yeah, the FE exam, they don't like the laptop, so yeah, I hear you.
They don't like most of the calculators either.
No, they don't. Yeah, you have to have a basic calculator maybe for the FE exam, I don't know.
Yeah.
Or at least a simpler one.
There's 5 calculators that are accepted,
A
I think.
couple acceptable ones.
Yeah.
All right, so what are some other things you can do? You can do limits. Let's say I have 1 over x. What is the limit of y as x approaches infinity? It's 0. Isn't that cool? Okay. That's pretty neat, okay? And, I mean, you can even do what is the limit as it approaches 7. I mean, that's really easy. It's just 1/7, but the infinite one is a little trickier, okay? And I bring that one up, this whole thing about the limits, because there's a tricky part in the homework, okay? There's this homework problem right here, okay? And when I get a chance, probably not today, but maybe next time, I'll give a little bit more of a background of what's going on here. But here in this equation, there's this hyperbolic sign, which you've surely been told about sometime in some calculus class, right? I mean, someone will admit to that. The others will just have forgotten because you repressed that memory. But you've been told what a hyperbolic sign is, but you don't remember it, and that's okay because I never really remember what hyperbolic sign. But one of the interesting things about hyperbolic signs is that it's not periodic in the same way that a sine is. That if you take the hyperbolic sign of an infinite number, you get an infinite number. Okay, so it's not periodic like sine is. And so here we have a situation in this problem where w and h are constants. W is 2 feet, h is 3 feet, y is something that can change, that's a variable, and n is something, we're trying to do a summation. We're trying to do a summation over lots of n's at various different y points. Okay, so y is a variable and n is something that I'm trying to sum. So n could be different depending on which part of the sum I'm trying to do. So what I want to do is I want to set up a little piece here in MATLAB to handle this ratio here. Okay, because that ratio can be particularly nasty. Okay, so let me get my windows arranged here so we can see at least that ratio over there, that hyperbolic sine ratio. And what I'm going to do is I'm going to make so that y and n and f are going to be symbolic variables. I'm going to say w is equal to 2 and h is equal to 3. Those are the constants from that problem. So w and h are constants, n and y are things that might change. And I'm going to say that f is equal to the hyperbolic sine of n times pi times y divided by w, all divided by the hyperbolic sine of n times pi times h divided by w. Okay, so now f is a symbolic expression. It's this ratio here that's in the problem. Okay, and one of the things you'll notice is that, well, let me just do this. Hyperbolic sine of 0, that's 0. Hyperbolic sine of 1, that's something. Hyperbolic sine of 2 is something. Hyperbolic sine of 3. And as the value of the hyperbolic sine's input gets bigger, hyperbolic sine gets fast very quickly. Okay? So obviously hyperbolic sine of 60 is ridiculously big. Okay? And you'll notice in this equation that n has to go to infinity. This is an infinite sum. I'm supposed to make n go to infinity. So n in this equation, f, can get quite big. So n is going to get quite big, okay? And y in this problem, you'll find when I talk more about that problem, but y can actually vary between 0 and h. H is the height of some domain, and y can vary from 0 to h. So y can be any number between 0 and h, and n can be any number between 0 and infinity. Okay? Now, when y, let me take this hyperbolic, let me take the limit of f as y approaches h. Well, let me do 0 as y approaches 0. So the limit of f as y approaches 0, because the smallest value y can be is 0. So the limit of f, the limit of this thing as y approaches 0 is 0. Now that kind of makes sense because the hyperbolic sine of 0 is 0. So if y is 0, then the numerator is going to be 0. It doesn't really matter what's in the denominator, as it's going to be, it's going to end up 0. So that makes sense. The limit of f as y approaches 0. Okay? Now, the limit of f as y approaches some other number, say 1, that's not 0. Okay? Basically, they just took the y there and they replaced it with a number 1, and that's all that's really been changed. Okay? Now, if I take the limit as y approaches 1, and then I take the limit of that as n approaches infinity. So notice what I did. I'm taking, first of all, I'm taking the limit as y approaches 1. Okay? Then the result of that, which is this thing right here, I'm going to take the limit of that as n approaches infinity and let's see what happens. Okay? And as it turns out, that's also 0. Okay? Now, that's going to give me 0, and as it turns out, if I put even 1.5 in there, the limit of, if y goes to 1.5 and n goes to infinity, that's going to be 0. Okay? And as it turns out, no matter what y I put in here, it goes to 0. Okay? And sort of the reason is if you look at this thing here, you know, both the numerator and denominator are actually going to infinity because n is getting infinite. But when y is smaller than h, because h is 3, remember, when y is smaller than h, even though both go to infinity, the numerator goes to infinity more slowly because y is smaller than h. Okay, so it's kind of interesting. Now, one of the things that is different, though, is that if I take the limit as y approaches h, and then take the limit as n approaches infinity, suddenly that limit is different. Now, this makes total sense, too. Because if y is h, if you just take y here and replace it with h, then the numerator and the denominator are exactly the same thing. So it would make sense that even though it's infinity over infinity, they're exactly the same infinity, so it should go to 1. Okay? Now, if y is anything smaller than h, then even though the numerator goes to infinity, it goes to infinity more slowly than the denominator because y is less than h. So anytime y is less than h, I get 0 for that ratio when n goes to infinity. And anytime when y is equal to h and n goes to infinity, I get 1. Okay? So in this problem, you'll find that it's not really possible to solve it symbolically, because in this problem, basically you have x and y. X and y are varying, and then you have to do an infinite sum for every x and y pair, and you can kind of solve this symbolically if you wanted to, but it would be ridiculously slow. If you tried to use the symbolic math toolbox to solve this problem, it would be really, really, really slow. So you're not going to want to use the symbolic math toolbox for this problem, but I used it here to help me with the limits so that I understand what's happening with this ratio. And as you work into this problem, you'll find that it's important to know that when n goes to infinity, that this thing is going to be 0 unless y is equal to h, and then it will be 1. Okay? So we use the symbolic math toolbox to kind of help us get some information, and you could. I did. I went and solved that problem with the symbolic math toolbox, and it took like 30 minutes to solve the problem, when if I just do it without the symbolic math toolbox, just solving it numerically, it took, 10 seconds or something. So don't try to solve that problem symbolically. It'll just take a really long time. Okay? All right. So we've talked about the solve command, factor, expand, the limit. We can also do differentiation and integration in this, which is really great. So let's go back to, say, y is equal to sine x. And let's say I wanted to take the derivative of y. Well, that's cosine of x, right? Derivative of sine of x is cosine of x. Really handy, really nice. Okay? I mean, if I do something more complicated, well, not necessarily more complicated. Let's say x squared minus 6 times x plus 7. And I take the derivative of y, that's going to be 2x minus 6. So I can use it to take derivatives. Okay? I can also have it do integrals. So if that's my y, and I take the integral of y, okay? Oh, isn't that interesting? So that's apparently, that's not how I would think of it, as being 1/3 x cubed minus 3x squared plus 7x, right? That's how I would have thought about it, but that's how they wrote it, okay? I don't know, maybe I can, if I expand that, maybe there, now it's in the form that I was expecting it to be. Yes?
Type in pretty and still.
Yes, there's also pretty. So I can expand it. I can also do pretty on it, which will make it look like that. So let me show what the original one was. The original one was this, And then here, it like even put the squared sort of as a superscript and put a denominator for underneath there 3. Now that's still not in the form that I would think of it normally unless I did the expand part. But yes, pretty can very often make it look nice so that you see the equation in a better way. Okay, so that's a really good suggestion, pretty. Thank you. Yes? Right, so this is a indefinite integral, okay? So yes, it's leaving off the constant of integration. It's looking at just as the indefinite integral. Now that leads us to another point though, is that we can do this integral and specify what the bounds are. I can do it from a bound from 2 up to 3. Okay, and then it gives me an actual answer. This is the integral of y, which the integral of x squared minus 6x plus 7 from the bounds of x equals 2 to x equals 3. So if I don't want the indefinite integral that is missing the constant of integration, you're right, okay, I can actually have it do a bounded integral with a definite integral and give me an answer. Now again, notice when I do that, the result, ants, is still a sim. And if I want the actual number for that, I need to convert that sim into a double. There. Now I have it as a numerical value rather than a symbolic variable. Okay? So, really great. I mean, it can do limits, it can do differentiation, it can do integration, it can do all sorts of, polynomial manipulation. It can even, this is one I forgot to do earlier, it can solve systems of equations. Okay? So, let me create f1, f2, x, and y as symbolic variables. And I'm going to make f1 be 3 times x minus 2 times y equals 8. And I'm going to make f2 equal to a different one. Let's see, negative 2 times x plus 5 times y equals negative 3. So here I have two equations in x and y, f1 and f2. And if I use the solve command again, I pass to it these two equations, and it returns something. Now this is kind of interesting, and I didn't really think about this. Our next lecture is going to talk about structures, okay, and cell arrays. And so the result, the return of this is actually a structure. Now that word structure is the same thing as the word structure that we were using in C++. And you remember I said we're going to talk about structures in C++ because there's the same thing in MATLAB. Okay? Now in MATLAB a structure can only have data members. It cannot have member functions. Now there is a way of doing object-oriented programming in MATLAB. I'm not torturing you guys with that. Okay? But we will talk here about structures. So let me go ahead and I'm going to say I'm going to give a z equals so that I catch this somewhere other than ants. And what it's saying is that this structure has what are called fields, which is just the MATLAB way of talking about a data member. So a field is a data member. So as a data member x and a data member y. And the way we access that is the same way as in C++. I have my structure z, and I have my data member x, so if I do z.x, that will tell me what the x data member is, and the z.y will tell me what the y data member is. So the answer to this, f1 and f2, those two equations, the solution for x and y are x equal to 34/11 and y equal to 7/11. Wow, wasn't that funny? 7/11. Didn't even plan that one. Okay? So this is really neat. You can solve systems of linear equation. Man, isn't that nice when you take linear algebra? Here you just plug in what the equations are and it'll tell you what. You don't even have to do all that Gaussian elimination and partial pivoting and all that mess stuff. MATLAB will give that for you so you can check your answers at least in your linear algebra class with MATLAB. Okay? So like I said, this is a really great tool to solve all sorts of stuff that you're going to need in your math classes. But again, like I said, most of the things in real world are going to be like this. Okay? Most of the things are not going to have symbolic solutions in the real world. Okay, so eventually if you're going to do lots of if you're going to have a calculation intensive type job, or if you go to graduate school or that sort of thing, you're going to have to start solving some things numerically. Now this course did have more numerical type stuff in it before we did Python, but I think it's better for us to move on to Python here rather than doing more numerical methods. But just be aware that, you know, doing integration and differentiation as an approximation is also out there. Okay? All right. Let me, in the last 12 minutes that I have, let me go and talk a little bit about this homework problem, problem number 3. Now, this problem is intended to be solved with the symbolic math toolbox. Okay? I do intend for that to be used in this one. Okay? And specifically, okay, there's this equation here, this equation in z. And we're going to need lots of different partial derivatives of z. We're going to need derivatives of z with respect to different variables in there. Okay? So I need to know, for example, how much does this z change with respect to u? Okay? And how much does that z change with respect to different variables? Okay? So what I'm going to do is I'm going to show you how to do that. Okay, there we got our equation. And just to be safe, I'm going to go ahead and clear, start fresh. And I'm going to create symbolic math variables for z. I'm going to create a symbolic variable for u, x, v, y, and b. So all those things I'm going to have as symbolic variables. And I'm going to say that z is equal to 1 divided by 1 plus the exponential of -1 times u times x plus v times y plus b. Okay? So I just copied over this equation. I made all the things in it symbolic variables. And I now typed in the equation. And so now I have z as that. And like somebody was saying, I could say pretty z, make z look pretty. There's pretty z. Okay? So it looks a little prettier. So that's another way to look at it. Okay? Now, I don't know, where do you guys do partial derivatives? Is that in Calc 2? 3? Okay? So some of you have never heard of a partial derivative, right? Okay. You're normal. Don't worry. Okay? The concept is really easy. Okay? I mean, if I had this equation and u, v, y, and b were constants that I knew. Let's say u had the value 2, and v had the value 3, y was the value 5, and b was the value -4. If those were constants, and I said take the derivative of z, you would take the derivative of z with respect to x, and you would assume that those other things are their constant values. So their derivatives are obviously 0, and use chain rule or whatever. They're constants, you just leave them alone when you take the derivative. Okay? And so if I'm going to take the derivative of z with respect to x, okay, there it is. Okay? I mean, taking the derivative of this with respect to x, you have to do the quotient rule and then the chain rule, and it's not hard, it's just painful. There's a lot of steps. Okay? So here, this assumes that u, b, v, and y are all constants, and x is the only thing that changes. And so it took the derivative of that with respect to x. So isn't that wonderful? Okay, I now have the derivative with respect to x. Now, I could say, well, hold on. You know what? Now, let's assume that x is a constant along with b, v, and y. Let's say b, x, v, and y are all constants, and u is now the thing that could change. It's not a constant anymore. The other things are constants. And so now I'm going to take the derivative of z with respect to u, assuming that all the other variables are constants and can't change. So there's the derivative of z with respect to u. You know, there's some similar things in there. Well, it's actually very similar to the x one because u is just multiplied by x, so it hardly looks any different just because of the symmetry of u and u and x. Okay? So let's do another one. What's the derivative with respect to y? You know, that one looks a little bit different. Or it does. Yeah. Oh, yeah, here, look. There was one difference. the u and the x one, it looked all the same, but there's a different u is out front instead of x out front. And here now the v is out front. So it all just sort of depends. And you can check that. If you want, you can go and do the derivative yourself and check that that is actually the answer. Okay? Yes, question. Somebody have a question? No? Good. Okay. Now, let's say we want, let's say we take the derivative and let me go ahead and put it back to the x1 and say I'm going to name this the variable dy dx. Okay? So I've now stored it not in ants, but I've stored it in dy dx. Now let's say we now know the values of each one of these things. Let's say b happens to be 2, u happens to be -3, x happens to be 6, and y happens to be -2. Okay? So I maybe now want to evaluate what is the derivative dy dx at given values of all the things in there. I might want to know that. So what I can do is I can now set b, u, x, and y to actual values. Now notice, those things are now no longer sims, but now they are doubles. Y is still a sim, z is still a sim, and dy dx is still a sim, okay? But now I've given values to those things. Dy dx, that's what dy dx is. Those now have values. Now what I want to do is I want to substitute the values of those things into the expression. So if I do subs for substitution, so substitute all of the things in for dy dx. So what it's going to do is going to look, well, what is the value of b? That happens to be 2. What is the value of u? That happens to be -3, etc. And it's going to take those values and it's going to plug them in. Look, I never said what v is. So it replaced all of the things except for v because v is still a symbolic. Okay? So I think I meant to give v a value. Let's give it the value of -1. And let's do the subs again. So now you can see it's substituted in all of the values, and it's still a symbolic expression. It's not giving it to me as a numerical answer because it's giving me the exact analytical number. And if I wanted that to be an actual number, then I would do double of that. Okay? And as it turns out, that number is quite small, close to 0. It's not exactly 0. But it's close to 0. All right? So what I did here is I started off with my function z. I took a derivative of it. Okay? I took a derivative of it. Then I set all of the values that I wanted the things to have, including v. And then I substituted in all the things for that and converted it to a double. What's that?
It came up with something different that time.
I don't know. Did I give it v? Yeah, I don't know. Isn't that interesting? Something's different. Oh, I know what it is. Well, I think, It is interesting why it's different. Let's see, what is diff of z with respect to x?
Oh, 62.
I think it must have to do with something that before these x, u's, v's, they were all symbolic things before. I wonder if that is playing a role.
I think it took another differentiation of it.
Yeah, I did something differently. And that's sort of why you want to always clear when you start stuff over again, so you don't have other stuff that's in there. But again, the main idea is that I'm starting off with some function. I differentiate that with respect to one of the variables in the function. Then I set values for what I want the things in that function to have. I substitute in for it, and then I convert the symbolic thing into a double, and then I get an actual number. Because most of the time, in the end, you're trying to have an actual number to solve something. Okay?
So what if you would have subbed and then solved?
If I subbed and then did the diff?
No, then did solve after doing the diff.
Well, we haven't used solve here at all. So I'm not trying to solve an equation here. I'm trying to substitute values into a function. So it's a little different. I'm not trying to solve anything. I'm taking the derivative and then replacing the variables in there with numbers. Okay? So let me do a simpler thing with the subs. Let me say, let me do clear now. Clear sims y and x. And I'll say y is equal to x squared plus minus 7 times x plus 5. Okay? And here I could say x is equal to 2 and then substitute into y. And so I started off with this as a symbolic equation. Then I set x equal to a double and then substitute it in. So that's the same thing as doing 2 squared minus 14 plus 5, and the answer is negative 5. Okay? And I think what the problem was that when I tried to recreate it before is then I tried to do something with this expression where x was no longer a symbolic thing, it was now a double, and I tried to recreate it when x was not a it was a double and not a symbolic. I think that's why I got a different answer with that thing before.
I guess what I was really kind of asking, so when you subs and it gives you a complete linear function outside of the EXPs,
what subs will do is it'll look and see of all the things that y depends on, it'll find is if x is a double, it will replace that number in there and reevaluate the symbolic expression.
That was my underlining.
Okay, so let me do, it's time to go, but let me do one more thing. Let's have z be a function of x and y. Okay, and if I now set x equal to 2 and do subs into z, the x will be replaced by 2, but the y will remain a symbolic variable. Okay, because y still exists as a symbolic variable. Y is still a symbolic, x is not a symbolic, so when I subs, it only substitutes the x in there. Okay, so I'm going to go ahead and